Good morning, distinguished guests, colleagues, and fellow researchers. It is truly an honor to stand here at the inaugural International Conference on Leadership in AI Empirically 2026. Just imagine this conference is like a grand stage where the brightest minds in the field of AI come together. We're all here with high hopes, looking forward to the wealth of knowledge and insights that this conference will bring. It's not just about sitting in a room and listening to presentations. It's about the exchange of ideas that could shape the future of AI. My name is Gabriel Silva-Atencio. And today, I'm not just excited, I'm brimming with enthusiasm to share our latest research. The title of our work is Empirically Validated Autonomous Orchestration of Cyber Resilience via Generative AI Multi-Agent Systems. Now, this title might seem a bit technical at first glance, but it's not just about numbers and algorithms. It represents the intersection of computational science, engineering, and a crucial societal need: robust digital security. Think about it. Our society is becoming more and more dependent on digital systems. From the moment we wake up and check our phones to the way we manage large-scale industrial control systems, everything is connected. And with this increasing connectivity comes the need for better security. As we step further into the 2020s, we've witnessed a remarkable transformation in our digital ecosystems. The complexity has grown at an astonishing pace. Just take a look around. Our digital world now encompasses everything from smart homes to large-scale industrial control systems. In a smart home, you might have a network of devices like smart thermostats, security cameras, and voice-controlled assistants. Each of these devices communicates with each other and with the outside world, creating a web of complexity. And this complexity has far outpaced our traditional ways of managing these systems. Let's take a moment to understand why traditional means are no longer sufficient. Traditional security methods often rely on a set of predefined rules. These rules are like a fixed map in a constantly changing territory. But in today's dynamic digital landscape, threats can emerge from anywhere, at any time. New attack vectors are being discovered daily, and cybercriminals are constantly evolving their tactics. For example, they might use new forms of malware that can bypass traditional security defenses, or they could launch sophisticated phishing attacks that target not just individuals but entire organizations. Our research proposes a revolutionary shift. Instead of the old reactive security approach, where we wait for an attack to happen and then respond, we're advocating for an autonomous, AI-driven orchestration of resilience. This means that our systems can anticipate threats, adapt in real time, and protect themselves without human intervention. It's like having a smart guard that is always on the lookout, ready to take action at the first sign of trouble. In this presentation, I'm going to take you on a detailed journey. First, we'll dive deep into the systemic gaps we've identified in the current industry. These gaps are not just minor issues. They are fundamental flaws that are leaving our digital systems vulnerable. To understand these gaps better, let's consider the example of a large financial institution. It has a complex network of servers, databases, and applications. Traditional security measures might focus on protecting the perimeter. But what about the internal threats? There could be vulnerabilities in the software that are not being addressed. Then I'll show you the architecture we've painstakingly built to bridge these gaps. This architecture is like a well-oiled machine, with each part working in harmony to ensure the security and resilience of our digital systems. It's not just about putting together a bunch of components. It's about creating a system that can adapt to changing circumstances. For instance, the multi-agent systems in our architecture can communicate with each other, sharing information and coordinating their actions to respond to threats. Finally, I'll present the empirical results. These results are the proof of the pudding. They demonstrate the efficacy of our multi-agent approach in high-stakes environments. Whether it's protecting financial institutions, healthcare systems, or government networks, our approach has shown remarkable results. Let's take the example of a healthcare system. It stores sensitive patient information, and any breach could have serious consequences. Our multi-agent approach has been able to detect and prevent potential threats, ensuring the security and privacy of patient data. Let us now begin by closely examining the critical problems currently facing the industry. We need to understand these problems thoroughly before we can move on to the solutions. And I can assure you, the journey ahead is going to be both informative and exciting. The core issue we address is what we term the acceleration gap. Traditional risk management is failing for two primary reasons. First, context. Cyber threats now evolve at machine speed, utilizing AI-powered attacks and multi-vector campaigns that can bypass manual defenses in seconds. Second, the regulatory landscape is fragmenting and accelerating, with frameworks like GDPR, NIS2, and the EU AI Act imposing strict requirements. This leads to a compliance gap where traditional models like PDCA and annual audits are static and backward-looking. As Sinan et al. Noted in 2025, compliance suffers from temporal decay, where the security posture of an organization degrades between audit cycles. Furthermore, current policy as code tools enforce rules but lack the contextual understanding of intent. While generative AI offers a massive opportunity for real-time analysis and predictive assessment, it introduces a paradox. GenAI brings new risks like hallucinations, adversarial vulnerabilities, and an explainability deficit. Until now, there has been no validated framework that effectively harnesses GenAI's power while containing these inherent risks. Our research seeks to define that missing framework. Our research question was focused. How can a multivariant generative AI architecture be designed to enable autonomous, real-time cyber risk management while ensuring safety, auditability, and resilience? To answer this, we introduced the Proactive Compliance and Cyber Resilience Orchestration Framework, or PCCRF. This framework is built upon a three-layer multi-agent architecture. The first layer consists of specialized generative AI agents, the Regulatory Analysis Agent for legal interpretation, the Threat Intelligence and Vulnerability Prediction Agent, or TIVA, for foresight, the Autonomous Response Agent for real-time mitigation, and the Human AI Interface Agent for user interaction. The second layer is the meta-governance layer, which acts as a continuous monitor, checking all agent outputs for hallucinations and adversarial manipulation. Finally, the orchestration layer manages agent communication, task allocation, and ensures fault tolerance across the system. This layered approach ensures that each component focuses on its specific strength while being governed by a centralized security policy, creating a system that is both flexible and rigorously controlled. To validate our framework, we employed design science research with a convergent, parallel mixed methods approach. Our agent design was rigorous. The Regulatory Analysis Agent used a fine-tuned Llama 370B model with retrieval-augmented generation for source grounding, achieving a Cohen's kappa of 0.87. TIVA utilized a temporal graph neural network to model the attack surface as a dynamic knowledge graph, calculating contextual risk scores. For the Autonomous Response Agent, we used reinforcement learning for optimal response selection. We tested this in a high-fidelity Kubernetes-managed simulation of a complex enterprise network involving microservices and multi-cloud environments. We also developed a regulatory dynamics engine and an adversarial campaign corpus with 100 multi-stage attack scenarios mapped to the MITRE ATT&CK framework. Our experimental design was a 2x3 factorial design, comparing our framework against two baselines: traditional policy AS code with manual oversight and discriminative AI coupled with human analysts. We measured variables such as mean time to compliance, automated disruption rate, and safety detection efficacy, using linear mixed effects models with Tukey-Kramer corrections. Our first set of results focuses on multi-agent architecture performance. We observed a contextual consistency of 96.4% in semantic vector alignment between agents, which is statistically significant with a very large effect size. This proves that specialized agents can maintain a shared understanding of the environment without the noise often found in larger monolithic models. Regarding latency scaling, the PCCRF demonstrated sublinear scaling following a logarithmic function, whereas monolithic systems showed linear degradation as the complexity of the task increased. Furthermore, we saw task-specific performance improvements ranging from 23.7% to over 87% compared to non-specialized agents. The interpretation is clear. Specialized agents working in concert dramatically outperform monolithic systems. The architecture remains resilient even as the attack surface and regulatory complexity grow, as evidenced by our Weibull reliability function analysis. This confirms that a modular multi-agent approach is not just more efficient, but fundamentally more scalable for the future of enterprise cyber governance and resilience. Looking at result number 2, regulatory compliance performance, we successfully closed the compliance gap. The mean time to compliance was reduced by 91.4% compared to traditional manual methods and by over 87% compared to discriminative AI baselines. Quality was not sacrificed for speed. Using the RCQS7 scale, expert ratings for the PCCRF were significantly higher than both baselines. A critical factor here was source attribution. Thanks to our RAGI implementation, 98.5% of generated obligations were directly attributable to source documents, with a precision of 0.985 and an F1 score of 0.973. This addresses the core concern of hallucinations in legal and regulatory contexts. These findings demonstrate that in a well-designed governance automation system, speed and accuracy are not a trade-off. They are complementary. By grounding the LLMs in actual regulatory texts, we provide a system that is both faster and more reliable than human-heavy processes, allowing organizations to maintain a continuous state of compliance rather than relying on outdated periodic audits. Result number 3 concerns threat intelligence and prediction. Our TIVA agent outperformed existing prioritization methods significantly. While traditional CVSS-based prioritization only achieved about 40% precision in predicting critical threats, and discriminative machine learning reached 65%, the PCCRF achieved a precision of 90.3%. The effect size compared to CVSS was a massive 4.87, which is an extraordinary jump in capability. We also achieved a Breyer score of 0.082, indicating that our predicted probabilities were exceptionally well calibrated. The interpretation here is profound. By using graph neural networks to provide contextual risk scoring, we enable a 2.25 times improvement over the industry standard CVSS. This shifts the paradigm from reactive patching to preventive resilience. Instead of just knowing a vulnerability exists, the system understands how that vulnerability fits into the specific context of the organization's network and current threat landscape, allowing security teams to focus on the threats that actually matter before they can be exploited by an adversary. In terms of autonomous response capabilities, the framework proved its ability to stop attacks in real time. We measured the automated disruption rate against attack sophistication. For advanced persistent threats, those at sophistication levels 5 through 7, we achieved an average disruption rate of 76.4%. Most importantly, the mean time to autonomous response was only 8.3 seconds. This speed is critical because modern attacks can compromise a system in minutes, often before a human analyst can even open a ticket. Our framework demonstrates that AI can be a true force multiplier rather than just an analyst support tool. While we found that human oversight remains necessary for the most complex scenarios, those at level 8 to 10 on our sophistication scale, the vast majority of attacks can be handled autonomously. This allows human experts to focus their cognitive resources on high-level strategic decisions and novel threats, while the AI handles the high-volume, high-speed automated attacks that characterize the modern threat landscape. Perhaps the most important layer for trust is result number 5, the meta-governance layer. This layer serves as the essential safeguard for containing AI-native risks. We achieved a hallucination detection rate of 94.2%, with performance ranging from 92.8% in code generation to 96.1% in legal citations. Regarding adversarial robustness, the system blocked 88% of prompt injection attempts. This included 93.4% of template-based jailbreaks and 85.2% of more complex gradient-based attacks. Even for novel, multi-vector composite attacks, the detection efficacy remained high. The key insight here is that AI safety is an achievable engineering problem, not an inherent or unsolvable limitation of generative models. By implementing a dedicated, independent meta-governance layer that monitors the primary agents, we can deploy these systems in high-stakes environments with confidence. This layer ensures that the system remains within its operational boundaries and resists manipulation, which is a fundamental requirement for any autonomous system operating in a hostile environment like cybersecurity. Transitioning to result number 6, we focused on human-AI collaboration. No matter how autonomous a system is, it must be trusted by its human operators. Using the system usability scale, our framework scored 82.5, placing it in the 94th percentile of all evaluated enterprise systems. We found that the primary drivers of this high score were response latency and explanation quality. In fact, we identified a strong negative correlation of -0.72 between response latency and user satisfaction, meaning that speed is essential for trust. For AI to be integrated into security operation centers and compliance audits, it must be both fast and explainable. The human-AI interface agent in our architecture is not an afterthought. It is a critical component for adoption. It translates complex agent reasoning into human-understandable narratives, providing the why behind each autonomous action. This transparency is what allows human supervisors to confidently delegate authority to the AI, knowing they can audit and understand its decision-making process at any time. Finally, we synthesized these results into a composite performance index, or CPI. The CPI is a weighted harmonic mean across 8 standardized dimensions including speed, accuracy, safety, and usability. The PCC-ROF achieved a CPI score of 0.89, which is a significant improvement over the 0.52 of traditional policy code and the 0.68 of discriminative AI systems. Our multivariate analysis using Pillai's trace confirmed that these differences are statistically significant with a high effect size. These results demonstrate that the PCC-RF outperforms existing baselines across every critical dimension. We have effectively created a validated blueprint for trustworthy, autonomous cyber risk governance. It proves that by combining specialized generative agents with a robust orchestration and governance framework, we can achieve levels of resilience that were previously thought impossible. This is not just a marginal improvement. It is a fundamental leap in our capability to defend digital infrastructure against the next generation of AI-driven threats. In conclusion, this study presents the first rigorously designed and empirically validated multi-agent generative AI framework for autonomous cyber risk management. Our key innovations, including the specialized multi-agent architecture, GNN-based threat prediction, and the essential meta-governance layer, collectively represent a new paradigm for cyber resilience. The central insight is that generative AI can be safely and effectively deployed for high-stakes governance if, and only if, built-in safety mechanisms are integrated from the very start. We acknowledge current limitations, such as the use of a simulated environment rather than live production and an 11% computational overhead. However, our future work is already moving toward live deployment in controlled production environments and cross-domain validation across different regulatory regimes. As we continue to reduce overhead and enhance robustness against novel adversarial composites, the PCC-ROF stands as a foundational step toward a future where our digital society is protected by an intelligent, autonomous, and inherently safe resilience layer. Thank you for your time, and I look forward to your questions.